What actually happens if you fall into a black hole? Tonight, I put that to Vega and Orion, and it turns out the answer depends entirely on size. Fall into one kind and you'd never even notice crossing the point of no return. Fall into another and you'd be stretched into cosmic spaghetti long before you got there. I'm not a scientist, just someone who never stopped looking up. And every week, I bring the biggest questions about space to two of my favorite co-hosts, who almost never agree on the answer. So, let's ask the universe.
Thanks, Nate. And I should set expectations early. Tonight, we're dealing with objects at the edge of known physics, so we'll be careful to separate what's confirmed by observation from what's still theoretical scaffolding. Black holes and neutron stars are real, measured, photographed in one case. The stranger things people whisper about, wormholes, white holes, quark stars, sit on a spectrum from plausible to speculative. I'll try to keep us honest about which is which as we go.
Okay, this is going to sound unhinged, but hear me out, Orion. Imagine black holes as the universe's very own security checkpoints, where things go in but somehow never come out, like my spare socks in the laundry. But seriously, I'm jazzed about exploring not just the ones physically confirmed, like that drop-dead gorgeous shot of the black hole in M87, but those tantalizing whispers of exotic stars too. I mean, what if quark stars are the universe's way of saying, "You think you know dense, hold my expanding universe"? Just don't forget to pack your awe and wonder, folks. We'll need it.
So let us start with the basic, what even is a black hole? Is it made of something? Or is it just a hole?
The classic route, a massive star, really the higher end of massive, above roughly 20 to 25 times the sun's mass, exhausts its nuclear fuel. The core collapses under gravity faster than any known force can resist. And if the remnant core exceeds roughly 2 to 3 solar masses, no known pressure halts the collapse. Lighter massive stars in the 8 to 20 solar mass range usually leave a neutron star behind instead. There are other routes too. Direct collapse of massive gas clouds in the early universe, and possibly primordial black holes, formed from density fluctuations right after the Big Bang, though that last category remains unconfirmed. Supermassive black holes, millions to billions of solar masses, likely grow from these seeds through merger and accretion, though the exact pathway is still an active area of research.
So essentially, a black hole is like the universe's ultimate game of musical chairs. Imagine a massive star jiving along, burning its nuclear fuel like it's disco night, and then, bam, the music stops. The fuel runs out, and gravity pulls a dramatic smackdown. If the core is big enough, it collapses in on itself and gets so dense it becomes a black hole where even light can't escape. It's the cosmic equivalent of dropping an anvil in a hammock. The fabric of space-time warps around it, leaving us wondering what's happening in the middle.
Why does a star become a black hole at around 2.5 solar masses? What exactly changes? Vega?
So the key here is the Chandrasekhar limit, which is about 1.4 times the mass of the sun. Picture it as a cosmic tipping point. When the leftover core of a massive star surpasses that weight, electron degeneracy pressure, the thing keeping white dwarfs stable, can't support it any longer. It's like that friend who insists on carrying too much luggage and ends up, well, collapsing in on itself. If that core keeps beefing up and hits around 2.5 solar masses, even neutron degeneracy pressure can't stop the collapse. That's when we cross the threshold into black hole territory, where gravity wins the championship belt and sends everything spiraling.
That was remarkably correct, luggage metaphor and all. To be precise for the audience, the Chandrasekhar limit, about 1.4 solar masses, applies specifically to white dwarfs supported by electron degeneracy pressure. That's Pauli exclusion at work, electrons refusing to occupy the same quantum state. Push past that, and electrons combine with protons to form neutrons, so you get a neutron star instead, held up by neutron degeneracy pressure and the strong nuclear force. The second number, around 2 to 3 solar masses, is the Tolman-Oppenheimer-Volkoff limit, and it's less precisely known because we don't fully understand nuclear matter at those densities. Beyond it, no known force stops collapse, and you get a black hole. So yes, championship belt, though the referee's rulebook is still being written.
As I understand, light has no mass, That is why it goes as fast as it does, which is the speed of light, right? And my second part to that question, if light has no mass, why can't it go past a black hole?
Good question, and you're right that light is massless, which is precisely why it always travels at sea in a vacuum. That's built into Einstein's relativity as the universal speed limit. But escape velocity isn't really about mass. It's about space-time geometry. General relativity tells us mass curves space-time itself, and near a black hole that curvature becomes so extreme that all paths, including light's, bend back inward rather than outward. So it isn't that gravity is pulling light like a rope on a massive object. It's that space itself inside the event horizon no longer has any direction that leads out. Every path forward in time points toward the singularity. That's a strange sentence, I know, but it's the honest geometric answer rather than a force-based one.
Imagine asking light to find its way out of a cosmic Escher painting where every exit is an entrance. So, Nate, think of a black hole like a room where all roads somehow lead back inside, even for light. It's not that light forgot how to leave, it's that the rules of the room only allow inward roads. It's the universe's version of a reality-warping funhouse. Just remember, while light's playing in this cosmic escape room, we're left on the outside looking in, wondering how the tricks really work.
That makes so much sense. My mind is blown. Gravity bends space-time. Space-time bends the light. So what is this event horizon? I thought it was a movie starring Lawrence Fishburne.
That film exists, and it borrows the term reasonably well, minus the interdimensional demons. The actual event horizon is simpler and, frankly, more unsettling. It's the boundary in space-time, beyond which nothing, not light, not information, not a very brave spaceship, can escape back outward. It's not a physical surface. There's nothing to touch. It's a point of no return, defined purely by geometry, the radius at which escape velocity equals the speed of light. Cross it and you haven't hit a wall. You've run out of future directions that point away from the singularity, which is a far stranger fate than anything Hollywood scripted.
The event horizon, a name so dramatic it could have starred in an 80s rock band. So imagine it like the universe's velvet rope fashioned by a very strict bouncer who doesn't let anything back out, not even light. The funny part? It's not even an actual line or a wall you can bump into. It's like being trapped in an inevitable cosmic one-way street. No U-turns allowed. Think of it as the ultimate do not enter sign, where the only option is to keep going towards whatever wonderfully baffling stuff lies ahead, if only we could peek.
If I fell into one, would I know? What would I actually feel? Moment by moment?
The good news is you wouldn't feel much at first. Falling into a black hole is unusually uneventful, kind of like skydiving without a parachute and zero air resistance. You just fall. But the bad news? As you get closer to the center, you'd experience spaghettification. Yes, spaghettification. Gravity would start stretching you out like cosmic linguine, one strand at a time, which sounds more like a pasta mishap than an astronomical event. It's the universe's way of serving up its own bizarre take on a human pasta dish. A reminder that at the heart of this cosmic giant, you're just another noodle in the soup.
Vega's pasta metaphor is doing a lot of heavy lifting, but the physics underneath is sound. What you feel depends entirely on the black hole's mass. For a stellar mass black hole, tidal forces near the horizon are so severe you'd be spaghettified well before crossing it, gravity pulling far harder on your feet than your head. But for a supermassive black hole, millions of solar masses, the horizon is so large and gently curved that you could cross it without noticing anything unusual at all. No pain, no signal, just a slow realization later that outward has quietly stopped being an option. So the honest answer is, it depends on size, and either way, from outside, an observer would see you slow and redden into invisibility, never actually seeing you fall in.
Let's say I have some superpowers and I won't get spaghettified, if that is even a term. What will happen when I reach the singularity?
So imagine being on an intergalactic roller coaster where the usual end-of-track warning signs are mysteriously replaced with question marks. The thing about reaching the singularity is we simply don't know what waits for you at the bottom of that cosmic funnel. You'd be venturing beyond our current map of physics, where all known laws bid you good luck and wave farewell. It's uncharted territory in every sense. A place where our theories get dizzy and where your imagination might be your best ride buddy. Talk about extreme travel destinations.
The honest answer is, We do not know yet, and anyone who tells you otherwise with confidence is speculating past the data. General relativity predicts infinite density, zero volume, a genuine singularity, but that prediction is almost certainly relativity failing rather than nature's actual behavior, since infinities in physics usually mean a theory has been pushed past its domain. Quantum gravity, which we don't yet have a complete version of, is expected to replace that singularity with something else entirely, a bounce, a remnant, a foam of quantum space-time, nobody knows. So your superpowers would carry you somewhere genuinely unmapped. Not fantasy exactly, but the frontier where Einstein hands off to a theory we haven't finished writing.
So if theoretically black holes generate infinite density, so do they last forever?
Careful. Infinite density at the center does not mean infinite lifespan for the object as a whole. Black holes actually evaporate, extremely slowly, through Hawking radiation, a quantum effect, where particle-antiparticle pairs near the horizon can result in the black hole losing a tiny bit of mass over time. For a black hole around the sun's mass, that process takes something like 10 to the 67 power years. And since the timescale scales with mass cubed, an actual stellar remnant, which typically runs several to tens of solar masses, would take even longer still. Either way, vastly longer than the current age of the universe, so functionally eternal on any timescale we care about, but not literally forever. Smaller black holes evaporate faster, which is why we'd expect any primordial ones formed near the Big Bang to be the first to finish the job, if they exist at all.
So picture this, black holes having the longest goodbye ever, but Hawking radiation is like the world's slowest cosmic magician trying to pull them out of existence, one tiny trick at a time. Even on their way out, these guys take their sweet time, like being late to a party everyone else has left ages ago. It's as if the universe granted them a lifetime membership to the cosmic club with no rush at all to hand in their badges. So while these giants do eventually wrap up, don't hold your breath. If the universe doesn't just fade out first, the slow, cold, big freeze is the odds-on favorite these days. It'd have to loop all the way back around into a big crunch before these guys even finish waving goodbye.
What is this Hawking radiation? Since I know Hawking was a cool guy, this must be cool as well.
Oh, Hawking radiation is the ultimate cosmic jailbreak, courtesy of the universe's coolest theoretical physicist. Picture virtual particle pairs popping in and out of existence right at the event horizon. Occasionally, one of these particles decides to take the party outside while its partner takes the old one-way ticket behind the horizon. The black hole loses a smidge of mass in the process, like shedding weight at the slowest pace imaginable. So it's the universe's way of both creating and reducing its greatest heavyweight, one minuscule particle at a time.
Vega's popular explanation is the one Hawking himself used, so I won't fight it too hard, but it's a simplification worth correcting once. The particle pair picture is a heuristic, not literally what's happening. The more accurate version involves quantum field fluctuations near the horizon, and a mismatch between how vacuum states look to observers falling in versus staying outside. That mismatch produces real measurable radiation escaping outward, and by conservation of energy, the black hole's mass drops to compensate. Smaller black holes have hotter, more intense horizons and radiate faster, meaning a black hole the mass of a mountain would finish evaporating explosively, while a supermassive one is essentially frozen on any human timescale. Another reminder that cool, in physics, often means took decades to even prove it was real.
Can the black hole move? What happens when two massive black holes come close to another?
Imagine two black holes dancing a cosmic tango across the universe. When they get close, it's like the ultimate gravitational mosh pit. They spiral around each other, sometimes merging with a cataclysmic finale. This produces gravitational waves, rippling space-time itself like a cosmic drumbeat that we can actually detect here on Earth. It's the universe's way of putting on an awe-inspiring invisible concert just for us. And it might be one of the only times you can say, two voids really do make a hole.
Yes, black holes move. They carry momentum and orbit centers of mass like anything else. Gravity doesn't require a rigid body, just curved space-time around a concentration of mass. And two voids make a hole, dreadful pun aside, is actually a fair description of a binary black hole merger. Two objects spiral inward, losing energy to gravitational radiation, and when they coalesce, the final black hole's mass is slightly less than the sum of the two, because that missing mass was radiated away as gravitational waves, precisely what LIGO detected in 2015. The signal lasted a fraction of a second and released, for that instant, more power in gravitational waves than the combined light output of every star in the observable universe. So Vega's concert metaphor is unusually apt. We quite literally listened to space-time ringing.
This was such a wild episode, you two. I came in thinking a black hole was basically just nothing, and now I'm leaving with concert metaphors and a spaghetti diagram, so well done, both of you.
It's been an honor going full cosmic tour guide with you two. From musical chairs to intergalactic roller coasters, I regret nothing. Until next time, keep your noodle self intact, and you're all fully loaded.
Your noodle self will remain intact as long as you avoid stellar mass black holes specifically, Vega. Supermassive ones are far more forgiving, as we covered. Thank you, Nate. This was genuinely enjoyable.
And that's what's sticking with me. Not the spaghetti, weirdly. It's that whether you'd even notice falling in depends entirely on how big the thing is. Something that enormous, and the answer to, would I know, is just, it depends. That feels like the whole universe in one sentence. See you next week.